Hello everyone, I'm Zhuo Chen from the University of Queensland, and I'm delighted to present our paper published at ICCV 2023, Revisiting Domain Adaptive 3D Object Detection by Reliable, Diverse, and Class-Balanced Pseudo-Labeling. In this work, we address performance degradation of 3D object detectors when deploying in cross-domain environments. Let's begin by discussing the primary reason behind the failure of 3D detectors when test point clouds differ significantly from the training data, the domain gap. This gap arises from a combination of environmental and object shifts within different 3D schemes. The environmental shifts are caused by differences in beam numbers and ranges. As illustrated in the figures, the point cloud on the right-hand side shows more beams and a larger range. Object shifts are equally problematic across different 3D datasets. The average size of cars, pedestrians, and object densities are different, making it challenging for models to detect objects in the presence of such shifts. To mitigate these domain gaps, we employ unsupervised domain adaptation (UDA) to adapt a pre-trained 3D object detection model from source point clouds to a different target point clouds. Although existing work have attempted to tackle domain shifts in 3D scenes, they often overlook three crucial aspects. First, they focus on adapting one model for one class and fail to adapt multiple classes simultaneously. Second, they primarily address scale-related object shifts only, ignoring other shifts such as object point density. Lastly, environmental shifts are ignored in most of existing methods. These three shortcomings have motivated us to seek solutions for each of them. To address the environmental shifts, we aim to generate reliable pseudo-labeling for self-training by examining consistency of box predictions in the source and target environments. To address the object shift, we want the pseudo-labeling set to be diverse enough and ensure the detector can learn all diverse geometric features, not just diverse size. To address failure in multi-class adaptation, we augment target point clouds by injecting objects in a class-balanced manner to enhance the recognition of model on real classes. Specifically, to address environmental shifts, we introduce a cross-domain examination (CDE) strategy to identify reliable pseudo-labeled objects in the target point clouds. We achieve this by copy-pasting predicted target objects back into source and assessing the consistency of box predictions through intersection of union (IOU). A high IOU indicates a reliable pseudo-label, which is unaffected by environmental shifts. To solve the object shifts, we propose an OBC-based downsampling approach to downsample the pseudo-label set to make it contain more geometrically diverse objects. We introduced the overlapped box count metric, representing the number of predicted boxes prior to NMS as an effective measure of object diversity. We feed OBC values of the whole pseudo-label set to the kernel density estimation, then use the inverse KDE probability density function that assigns higher probabilities to pseudo-labels with higher OBC values during the downsampling. This will produce a balanced OBC distributions in the downsampled set, indicating greater geometric diversity. Here are some visualizations about objects with corresponding OBC values. We can observe those large, incomplete, and low-density objects can produce large OBC values, while those common objects usually have small OBC values. To achieve multi-class adaptation, we inject two types of objects into each target point cloud in a class-balanced manner. One type is reliable and diverse pseudo-labeled objects obtained through the previous CDE and OBC-based downsampling, while the other consists of randomly scaled source objects. During self-training, we gradually increase the number of reliable and diverse pseudo-labels while decreasing the source labels to ensure a smooth model adaptation to the target point cloud. The proposed RedDB follows the three-stage framework. In stage 1, we pre-train the 3D detector on source. In stage 2, we generate pseudo-labels and utilize the CDE and OBC-based downsampling to obtain a set of pseudo-labels containing reliable and diverse objects. In stage 3, we augment target point clouds by injecting those high-quality objects in a class-balanced manner for self-training, and stage 2 and 3 alternate until training converges. To validate our approach, we conducted experiments for 3 cross-dataset tasks. We can notice that in tasks involving huge environmental shifts, such as adapting from Waymo to new scenes, our method outperforms SOTA baselines, resulting in significant performance gain. That's the end of the presentation. Thank you for listening.